Hey, can everybody hear me?
Yeah.
Great. So there was a request during coffee that I remind you of symbols that were introduced last time. And I'm somewhat embarrassed by how many of them there actually are. And the number will not decrease, but I hope that this will be helpful in reminding you of where we are. And I've also written down the program that we embarked on last time, which is to recognizing that cosmic rays are a major constituent of diffuse astrophysical gas. How can we describe their interaction, exchange of energy and momentum in a way that's suitable for inclusion in large-scale models for the evolution of galaxies and galaxy clusters, which means deriving a fluid theory. And what we're going to see is that this fluid theory is based on kinetic scale processes, and there are at least two theories that are in wide use for how this works, and they give different results. And so in the end, it's an argument for really getting the kinetics right to do the fluid dynamics right. Okay, so hydrodynamics across scales. Questions from last time? Okay, so we had gotten about 2/3 of the way there. We had an MHD equation for the thermal gas, and it was I can see a potential flaw here. So rho gas partial U gas plus U gas dot grad U gas is minus the gradient of the thermal gas pressure plus the cosmic ray pressure plus the curl of B cross B over 4 pi minus rho gas grad phi. And although it's not obvious from the appearance of this, this is based on adding the momentum equations for thermal gas and cosmic rays together. And it's implicit in this that the parallel cosmic ray pressure gradient, C, is identically 0. So the idea is that the cosmic ray fluid has no inertia. So the only thing that can balance the Lorentz force is the pressure gradient. And since there's no Lorentz force parallel to the magnetic field, there can't be any pressure gradient along the magnetic field either. And so the implication of this is that cosmic ray pressure only acts in the direction perpendicular, acts on the thermal gas perpendicular to the mean magnetic field. And what we're now going to show is that the parallel component actually there can be a parallel pressure gradient, and it can act on the thermal gas. And this is going to take us on kind of a long and somewhat formal convoluted path. So I want to explain what's going on before we actually launch into the details. So the idea is that if we draw a magnetic field line in our gas, it has some small scale fluctuations that sit on it that I'm just kind of sketching in this schematic way. Oh, these things look very much like each other. So these are static magnetic fluctuations. And a cosmic ray that's describing a helical path along this magnetic field will interact with these fluctuations and come out. So since they're static, the magnitude of the particle momentum won't change, but the relative amounts of parallel and perpendicular momentum will change. So let's say it comes out of this with a slightly bigger gyroradius and a slightly smaller parallel velocity. And so we're going to describe this as a scattering process where P parallel, so now these are lowercase, this is not a pressure, this is a momentum. P parallel and P perp can change roles. And since conservation of momentum is component by component, if the parallel momentum changes, that parallel momentum must be taken up somewhere. And so delta P parallel for a cosmic ray is compensated by putting momentum or parallel momentum into the magnetic field and thermal gas. And so this must happen, but it's difficult to work out at a sort of microscopic level. So we're going to make a statistical argument, and that's where things get a little bit formal. But this is the basic idea, that the particles sort of find a loophole. There's no magnetic force parallel to the exact magnetic field, but there does wind up being a parallel force with respect to the background magnetic field because of the existence of fluctuations. So we'll say more later about where these fluctuations come from, and actually the important difference between these two transport theories arises in how they describe the fluctuations and their origin. Okay, but leaving that aside for the moment, let's describe the scattering. So let's let the angle between the particle momentum and the mean magnetic field, let's call that theta. And then there's a scattering rate which we can kind of write schematically as the mean of delta theta squared divided by time over some representative delta t. And it's convenient to go to a coordinate system where we describe a particle by its momentum p and its cosine, the cosine of its angle, the direction of momentum relative to that background magnetic field, which we're going to call mu. Okay, that's all I'm going to say for now. And well, no, that's not quite all I'm going to say for now. Then I'm going to say that the mean of delta mu squared over delta t is 1 minus mu squared d delta theta squared over delta t, which you can just see using the chain rule. Okay, so we have a scattering process. Now, the next thing we're going to do is introduce the distribution function f of p and x and t for cosmic rays, but we could do it really for any species, such that f d3p d3x is the number of particles in the volume d3p, d3x at time t. And then we can write down the Vlasov or collisionless Boltzmann equation for F in phase space. And it's this. Here's velocity dot df dx plus q E plus V cross B over C dot df dp. So this is the rate of change of F in X and P space. And if we're going to write it as equal to df dt collisions. So in the absence, so what is this collision term? df dt collisions represents changes in F due to random forces. And those random forces can be very general. They can be binary encounters with other particles, or in the application we're going to consider here, they're interactions with these magnetic fluctuations that we take to be random. And we're going to assume here that E and B are the average sort of DC quantities. Okay, so I'm trying to walk a fine line between being too formal and being too sketchy. So does this make sense? And does it seem, sort of credible? Yes, question.
So F is the distribution for the cosmic ray particles?
Yes, but I could write down a similar equation for any particle species.
I thought we have two species, like ions or protons. Oh no, it's mostly protons.
The cosmic rays are mostly protons. The gas is mostly is ions and electrons, basically. We could also include neutrals. This formalism can be generalized. But right now, I guess for consistency, I should put a C here on all these distribution functions. Yeah.
So these lesions are from the lesion static magnetic fluctuation.
We are yes. So we are going to describe the interactions with the static magnetic fluctuations as a random process. Not with other particles. Right. Okay. So maybe I should, in view of some of the questions last time, maybe I should say a little bit in general about how we derive fluid equations from starting with something like the Vlasov or collisionless Boltzmann equation. Yeah.
Usually when you write, so you've mentioned Vlasov, that's why I remember. So there is usually a term which is self-consistent. It depends on the density fluctuations of the particle species. If it's charged, it also gives a force on the particles itself. Do we consider that?
So we haven't said anything about how E and B arise, but we're going to assume that they're smooth. So fluctuations in E and B that arise from the proximity of other particles we would consider those to be binary collisions, and we would put them on the right-hand side. So these are smooth. I'm also dealing with the one particle distribution function. I'm assuming that the correlations between particles are not significant. So way back when, we could have started with a BBGKY hierarchy, but we're just talking about the one particle distribution function. Okay, so how do we derive fluid equations? So this will sort of allow me to make a point also. So the difference between the Vlasov or collisionless or Boltzmann equation and the fluid equations are that the fluid equations live in X and T space, and the Boltzmann equation lives in phase space, X, P, and T. So to derive fluid equations, we're going to integrate over P, and we're going to take what are called moments of that equation, which means multiplying it by various functions of P, powers, or other functions, and then doing our integral. So for example, let's integrate over phase space. Let me number these guys. I call this Roman numeral 1 and 2 and 3 and 4. Okay. So for term 1, the integral of, so I can take the time derivative outside, partial p of f d3p. So the integral of f over momentum space has a name. It has a name that we know. And what do you think that name is? Yes, it's number, exactly. It's number density. So it's all the particles at X regardless of their momentum. That's what we do when we integrate over momentum space. So that is partial n, partial t. Okay, so far so good. What about Roman numeral 2? So again, I can take the d by dx outside the integral because x and v are independent, they're just coordinates. So this is dot integral of f v d3p. Who does that have? What is that? How would you describe that? Say louder. Yeah, it's momentum. So let's define a mean velocity, which we were calling u. Let's define that as 1 over n times the integral of f v d3p. Okay, so then this becomes d by dx dotted with, well, fv is nu. Okay, that's term 2. What about term 3? So now we have integral QE dot d f dp plus q of v cross b over c dot df dp. d3p, what about that? Well, that's a very tempting conclusion, but let's think about it. Let's think about it carefully. Let's just look at this part. So I can write this as, since E is independent of P, and of course so is Q, I can write that as E dotted with the integral df dp d3p. And what is this? It's f at the boundaries. And I can choose my boundary so that it's 0. This is an exact differential. So this is 0. So anyone here who's ever taken a course from me, which I think is only one person, knows that when I write down fairly complicated math and ask a question, the answer is always 0, because I don't really expect you to do a lot of math in your heads. And the same goes for this term. You can show, you can integrate this by parts and use the anti-symmetry of the cross product to show that this term is also 0. And so now we're just left with term 4. So the integral df dt collision d3p is identically 0 if particles are not created or destroyed. Of course, they might be. But we haven't said very much about F. You know, if we're just going to use it to represent scattering from magnetic fluctuations, that will certainly conserve the number of particles, and so that will be 0. And so what we're just left with is partial n, partial t, plus the divergence of nu is equal to 0, assuming that particles are not created or destroyed. And that's just our equation of continuity. Okay, so it's early in the game, but we can start to recognize an insidious pattern here, which is that by taking the so-called 0th moment of the equation, namely multiplying the function of p that we multiply by is just 1, so we just integrated the equation, we got one moment, and then we got a higher moment. We got one involving v. And because of this v here in the advection term, and possibly the v in the Lorentz force, but it's mostly just the advection term, if we now multiplied, say, by p, took the first moment, we would have a pv here. So we would have a second moment. And if we just kept going, we would keep getting one more moment. So this set of moment equations is never going to close unless we figure out some way of truncating the hierarchy. And our choice is called our closure. And so if we assume that there are no third moments, that turns out to be equivalent to neglecting thermal conduction and viscosity, or we can make a model for thermal conduction and viscosity based, for example, on the Chapman-Enskog approximation, which is like a short mean-free path close to Maxwellian approximation, and get the kind of standard forms for thermal and viscous diffusion that we know and love. And we're not going to do that. But one way or another, we have to close this hierarchy if we're going to make any progress. Okay. So now let's get back to cosmic rays. Any questions about what we've done here? I mean, it's a very general discussion of how you derive fluid equations from kinetic equations. General and incomplete, yeah.
So if we multiply that equation by B, then we got the equation for the first moment.
Yeah.
And so I think similarly, so that would be similar to Navier-Stokes.
Yeah, yeah.
What do we get from the condition?
Ah, excellent question. So that depends on our model for collisions. So if we put in a full Boltzmann operator, we would get, yeah. So then the DFDT collision would have already some velocity terms in it. And we would have to break it down. And what would come out of it, actually, if we took it far enough, would be a viscous. Yeah. A place where this is done, actually, this is a great general reference. It's done for plasmas, but it's a great reference even if you're not working in plasmas. There's a paper by Brzezinski in 1965, and it's in what's now, I think, a defunct and obscure Soviet journal called Reviews of Plasma Physics. Volume 1. So they started out strong by having this incredibly great article that does all the transport in plasmas and many more things. Okay. So now let's get back to the cosmic ray scattering problem. So I'm going to make an assumption. We're going to assume variation only along B. We're going to drop E. And this is part of the MHD ordering. And we're going to assume that F is, I write the word down, gyrotropic. And what that means is that there's a random distribution of phase angles in the gyro motion. And under those conditions, if we assume these things and drop E, our Vlasov equation becomes partial F, partial T. Let me write that as the S direction. Partial F, partial T plus, and now things only vary along the S direction. So the only component that comes in is of the velocity is the parallel velocity. So V mu in our new notation is V parallel. Remember, mu is the cosine of the angle between the magnetic field and the particles. The Lorentz force goes away entirely. The electric part goes away because we said it did. And if F is gyrotropic, then V cross B dot grad P is 0. That's an exercise in algebra that, that you can do. So it all goes away. And it's just dF dt by collisions. And now let's assume dF dt collision is scattering in mu by static fluctuations and write it like this. Partial F, partial T plus V mu partial F, partial S equals d by d mu of nu times 1 minus mu squared over 2 dF du. So this 2 is, you'll see why it's convenient a little bit later. Okay, so we started with a very general and complicated looking equation and boiled it down by making these assumptions to a much simpler, but still somewhat complicated equation. Any questions or pushback on how we got here? Yeah. So nu can depend on space, it can depend on momentum, and it can depend on pitch angle. Just to emphasize and write all these things, nu is nu of x and p and mu. Could be time too, but for now, let's just make it nu. Okay. Yeah.
Why do you assume variation only happens in the parallel direction?
Because it's going to simplify the derivations that I do. It's not necessary. Yeah, it is not necessary, but since we're focused here on getting a parallel pressure gradient, I'm just doing it for simplicity. Okay. So mu is the cosine of the angle between the magnetic field and the particle. So this is just V in the S direction, the parallel direction. Okay, so in order to solve this, we're going to, by introducing, so think back. So remember we started this whole odyssey. Wow, I'm just covered with chalk. We started this whole odyssey by considering radiation, the propagation of radiation through a medium, and we assumed there was frequent scattering, short mean-free path, and we derived this expression for radiation pressure. We're basically going to be doing the same thing. Our discussion here is going to be based on the idea of frequent scattering, short mean-free path. So we're going to introduce 3 timescales, and we're going to assume to be widely separated. So what are they? The shortest one will be nu inverse And so this is the scattering time. So we're going to assume that on the timescales we're interested in which the system evolves, many, many scatterings occur. Then we're going to have an intermediate timescale, which I'll write as L over V, and V, it's just the length scale on which F varies, and V is approximately C, because we're talking about relativistic particles here. And then our longest time I'll write that as F over dF dt. So this is an evolution time for the system. So pictorially, what we're envisioning is something like this. So here's our field line. And our picture is that cosmic rays are zipping up and down this field line. So these short zigzags represent mean free paths. And cosmic rays are just scattering up and down the field line. I gotta stop. They're just scattering up and down the field lines. This is the mean free path. They're kind of running back and forth. So this is based on the observation that cosmic rays are very isotropic, at least in our part of the galaxy. No, they're not, streaming out of some identifiable source. They're just running back and forth. Okay, so how can that help us? Please, yeah. That's the scattering part.
Okay, so could you just give some intuition for the form of the collision?
Yeah. Oh, well, let me try to do that and let's see if it's what you had in mind. So, so here's our field. And here's our fluctuation. And it makes an angle, let me call it psi, with the mean field. Okay. So now a particle comes along and it sees this fluctuation and interacting with the fluctuation leads to some change, some conversion between parallel and perpendicular momentum. And I could write down the Lorentz force equation for it, but if the intuition is okay. Actually, if we thought about this, okay, so this works for biking, skiing, surfing, and possibly some other sport, okay? So let's do biking, because that's my favorite. So here's our field line. here's our field line. Okay, so you come along on your bike, and if the curvature in the field line is, or the curvature in the road is pretty gentle compared to your bike, you just keep biking along here. You hug the field line, okay? You come to something like this. This is kind of like washboard, and it hurts your hands a little bit, but it's just, you know, bumps in the road. You just keep going. Then you come to this. This is the width of your wheelbase, okay? This is the one you're going to have a big interaction with, right? And if it's a bike, so here we depart from magnetic fields, your total momentum is unlikely to be conserved, but it will be strongly affected, okay? Perhaps even reduced to zero. So, okay, so does that kind of help you visualize the scattering process? Okay, good. So, yeah.
So where does the magnetic fluctuation come from?
Ah, what a great question. So in the two theories that we're going to discuss, so in the theory that we're discussing now, we can think of the magnetic field fluctuations as part of some turbulent cascade in the interstellar medium or the intergalactic medium. In the second theory that we probably won't get to today, the fluctuations are actually made by the cosmic ray anisotropy itself. It's a self-regulated form of fluctuation. Yeah.
Yeah, so then I guess in the initial intuition you gave, so that there's then feedback to the thermal gases and the magnetic.
Yeah.
But I guess this term, we're only considering the effect on the cosmic rays.
So yeah, so that is a great question. So I think a way to think of this, is, sorry to bring up the biking again, but colliding with a bus, okay? So your momentum is enormously changed when you collide with the bus, and the momentum of the bus changes a little bit too, okay? But very little. To discuss this, to write down the interaction in the form that we did, we're ignoring the change in momentum to the bus. Good. Okay. So let's solve plus V mu partial F partial S equals D by D mu, nu 1 minus mu squared over 2 partial F partial mu sort of iteratively given the hierarchy of timescales. Okay, so to lowest order, df d mu, let's call that f naught. Df naught d mu is just zero. It's zero because nu is huge and there's nothing to balance it. This change due to the density in the field line, that's our intermediate time scale. This d by dt, that's our long time scale. This is our fast time scale. And so to the degree that this frequency is higher than any other rate in the problem, f must be isotropic by the same rate in order to balance it. So let's call that f naught. Okay, well, that was easy. Now let's go to next order. So to next order, we still don't consider d by dt, but we do have that advection term, which is that v mu df naught ds. Now f naught can be independent of mu, but it can depend on s. is d by d mu, nu, 1 minus mu squared over 2 df1 d mu. So df1, so f1 is the anisotropy of f, and it's smaller such that the product nu f1 is like f naught v over L. Yeah.
So why the noise over not given by the right hand side?
So this is, so you're saying f is so huge that I shouldn't have anything here at all. Is that what you're asking, or?
I mean, when you write down partial f now, partial mu equals 0, but I thought it's based on the written in the right hand side of the equation. So huge.
Ah, okay. Well, so let's, so I've been a little bit sloppy here. What I have in mind is something like f equals f naught plus f1 plus f. It turns out we're not going to have to go any higher than f1, and that the size of f1 over f naught, remember we're using these square brackets for sizes, is something like c over L nu. This is an assumption. Yeah, does that help a little bit?
No, I think my question is that I feel the zeroth order should be partial mu, and you have this function, because the function mu actually also depends on the variable mu itself, right?
It can depend on the variable mu itself, but I'm going to assume, or we're assuming, that for all mu and all p, it's large. Now, this does, it turns out this very probably does break down for the very highest energy cosmic rays. However, for the sort of gigavolt cosmic rays that we're developing this fluid theory for, it really seems to be good. I mean, we see that they're isotropic to, less than 0.1%. Okay, so now we have an equation for F1 in terms of F naught. So to solve this, let's go over here. So let's integrate this equation from some starting value, mu naught, to 1 d mu. Okay, so F naught is independent of mu, so the integral d mu of mu is just mu squared over 2, right? So this left-hand side becomes 1 minus mu naught squared over 2 v df naught ds, just from integrating mu. And then this one is even easier because it's an exact differential. So I just evaluate it at 1 and at mu naught. And at 1, of course, it vanishes. So I pick up a minus sign here. So nu times 1 minus mu naught squared over 2 dF1 d mu. Okay, well, the 1 minus mu naught squareds over 2 cancel. Bang, bang. And dF1 d mu then is just minus V over nu dF naught ds. Okay, so this satisfies the ordering that we assumed, but that's not such a great triumph because it's really by construction, but it also makes physical sense. So what does it say? It says that if F naught is, say, decreasing in the positive x direction, so if here's our field line, and we have lots of cosmic rays here, and relatively few over here, then on the average, there'll be a flux from the high density region to the low density region. That's really all it's saying. So here dF ds is negative, and we pick up this minus sign here. So it says dF d mu is positive, and so that means, so there's a positive anisotropy here. This makes sense? Okay. So now we're ready to use it. If we go to the next time ordering for the Fokker-Planck equation, we'll be able to derive an equation for spatial diffusivity. And we may not get there today, but if we don't get there today, we'll get there tomorrow. Okay, so now we're ready to derive the parallel force. Okay, so what is the parallel force density on the cosmic rays due to scattering? So let's take our scattering term. So d by d mu, nu, times 1 minus mu. So, okay, so let me back up a little bit. So we're going to take our equation, partial f, partial t, plus v, mu, partial f, partial s, is d by d mu, nu, 1 minus mu squared, over 2 df d mu. We're going to take this whole thing, we're going to multiply it by parallel momentum, p mu, and we're going to integrate it over p space. So that will give us an evolution equation for parallel momentum. And the piece we're interested in is this piece, because it's the parallel force due to scattering. So let's focus on this. Okay, so the integral of p mu d by d mu 1 minus mu squared over 2 df d mu there's a nu here. And now let me write down explicitly what d3 p is. It's p squared dp d mu. Okay, what should we do? Well, let's begin by integrating by parts in mu. So here we have this d by d mu here, and if we integrate by parts, we'll have d by d mu of mu, which is fairly easy. The surface terms vanish because the upper limits and lower limits are plus and minus 1. And so this will be minus the integral of p nu 1 minus mu squared over 2 df d mu. And it's really df1 d mu because that's as high as we went. And then this whole thing is p squared dp d mu. Okay. We happen to have an expression for df1 d mu. So we know that df1 d mu is minus v over nu df naught ds. So let's use that. So we have a minus here, we have a minus up there, so we get a plus. Nu d by d mu is just v, so we'll have a p, then we'll have a v, and then we'll have a 1 minus mu squared. df naught ds, p squared dp d mu. And f naught is independent of mu, so we can do the integral over mu. So the integral from minus 1 to 1 of 1 minus mu squared, there's a 2 here, over 2. So if we integrate the 1, we get 2, we divide by 2. If we integrate the mu squared, we get 2/3, we divide by 2, we get 1/3. So that is 2/3 times the integral of PV. Well, let's take the d by ds outside, d by ds of 2/3 PV f naught p squared dp, which also happens to be d by ds of the integral of PV over 3 f naught p squared dp d mu. Okay. So, does anybody remember the kinetic theory definition of pressure? Yes. And do you remember an expression for it from kinetic theory? I think you also had a hand up there. Or maybe it's down again. Well, this actually is pressure. It's momentum current, that's it. And it's 1/3 for an isotropic distribution. Because, it's a trace of the pressure tensor. So it's dPds, which is the parallel derivative of P. Okay. So this is actually what we set out to show. Scattering, that the scattering by magnetic fluctuations gives a force which is equivalent to the pressure gradient. And so what that means is that we can comfortably include a pressure gradient, a parallel pressure gradient, in our momentum equation for the thermal fluid. But they originate in very different ways. So let's write down the gas momentum equation again. Rho g partial UG partial T plus UG dot grad UG is minus the gradient of P cosmic ray plus P gas plus J cross B C minus rho gas grad phi. And let's remind ourselves of where this comes from. So the grad perp P cosmic ray comes from J cosmic ray cross B over C being combined with the gas current to give the total current, which we can then replace using Maxwell's equations, and the grad parallel of PC comes from scattering. By magnetic fluctuations. Okay, so we have a momentum equation for cosmic rays, or sorry, for thermal gas that includes cosmic ray pressure. Of course, we're not done. So at some point, we're going to also need an equation for P cosmic ray. So how do we determine P cosmic ray? So we're not done with kinetic theory. We're going to get it from kinetic theory. So let's continue with our kinetic theory by deriving a spatial diffusivity. Okay, so let's go back to our Fokker-Planck equation. So let's time scale, the biggest component, partial F naught partial T plus V mu partial F1 partial S. Okay, equals d by d mu times 1 minus mu squared over 2 dF2 d mu. So this is a little worrisome because obviously we can just keep doing this. We go to F3, F4. When do we get to eat lunch? Well, sooner than you think, because we're going to integrate this over our entire range of mu, -1 to 1. Okay. Well, so this is an exact differential. The quantity that's being differentiated vanishes from mu equals ±1. So the right-hand side will be 0, and we'll just get d by dt of 2 F naught. Let's put the 2 out here. So F naught is independent of mu. This term will take a little more care. D by ds take it outside, -1 to 1, V mu F1 equals 0. Okay, so F2, we wrote it down, but we don't actually need it. Okay, so it looks like we're getting close, but we don't actually have an expression for F1. We just have an expression for dF1 d mu. So let's write that as two partial F naught partial T. And now I'm just going to play a trick. Minus, we write this as minus d by ds integral from -1 to 1 of V, this is d mu, 1 minus mu squared over 2 d by d mu. 1 minus mu squared over 2 F1, because the derivative with respect to mu of 1 minus mu squared over 2 is just minus mu. And that's why I changed the sign. So that equals 0. Now we can integrate it by parts. 2 dF naught dt plus d by ds integral -1 to 1 v 1 minus mu squared over 2 dF1 d mu equals 0. So now I have dF1 d mu, and I do know what that is. So now 2 dF naught dt minus d by ds integral -1 to 1 v 1 minus mu squared over 2 dF1 d mu is minus v over nu dF naught ds. So I get another v. I get a nu down here, dF naught ds. Okay, so now let's define say what? Oh, yes, they are. Thank you. Okay, so now let's define kappa. It's kappa parallel because that's what we're doing. Kappa parallel is defined as the integral from -1 to 1. We can divide through by 2 of v squared times 1 minus mu squared over 4 nu d mu, which just happens to be what we have here. And then we have partial F naught partial t minus d by ds kappa parallel dF naught ds is equal to 0. Okay, so we derived a diffusion equation based on our assumption of frequent scattering. Now, if nu is independent of mu, which is certainly not always the case, then kappa parallel is v squared over 4 nu times the integral minus 1 to 1 of 1 minus mu squared d mu, which is, the integral is 4/3, so it's just v squared over 3 nu, which is also lambda v over 3. So it's exactly what, you know, one tends to write down for diffusion coefficients from random walk arguments. Okay, so we've seen how this frequent scattering assumption has led us to an expression for the parallel force and the parallel diffusivity. The next step is to consider fluctuations that are not static. So the next step will be fluctuations that move with the fluid velocity u. We don't have time to go through it today. Yeah, question. Yeah, let me explain that. So it'll turn out that the most efficient scattering occurs for fluctuations which satisfy a so-called resonance condition with the gyro motion. And so what that will mean is that particles with pitch angles closer and closer to 90 degrees, even if they have the same momentum, will be scattering off shorter and shorter wavelength waves. So the dependence of nu on the pitch angle, mu, will come about because there will be different amounts of power in waves of different wavelengths. And typically, there'll be some very short wavelength where there's essentially no power because of thermal damping or something else. And so so it's the dependence of the intensity of fluctuations on wavelength, which then prints through the resonance condition to a dependence on mu. Does that make sense? Okay, we'll discuss it a little bit more tomorrow. Okay, good. So the situation that we'll be considering is, here's our field line, here's some fluctuation, then we move some distance, here's another fluctuation, and if this fluctuation is moving with some speed u of x, and this fluctuation is moving with some speed of u plus delta x, and we have a particle, just for simplicity, imagine it bouncing back and forth between these fluctuations, it will either be gaining energy if the fluctuations are moving together, because u of x plus delta x is less than u of x, or losing energy if they're moving apart. And so the fluid velocity and its spatial dependence will leave its imprint on the evolution of the distribution function. And that is our last step in deriving this so-called Parker transport equation. So let's use the last few minutes for questions, and we'll take this up again tomorrow. So any questions? Yeah.
Do we have the gas which is basically neutral, and then we have the concentration of the proton? So I guess there was something compensating.
Yeah, so I can say a little bit about how that works. So in the interstellar medium, only a fraction between 10 to the minus 10 and 10 to the minus 9 of the thermal electrons have to balance the cosmic ray current. And that can be, it turns out that how that's done doesn't really matter very much. It can either be that you shift the whole electron distribution by 1 part in 10 to the 10, or you just extract, a little fraction of 10 to the minus 10 of the electrons, you have them moving, essentially with the cosmic rays. This actually breaks down in regions of very high cosmic ray flux, which may be representative of the cosmic ray acceleration process itself, which is near supernovae. And then it turns out there's a whole other class of instabilities that are caused by that affect waves that are shorter in wavelength than the cosmic ray gyro radius. And so the cosmic rays don't see them, but the electrons that are canceling their current do. And this leads to a kind of kinking of the magnetic field. We may not discuss that, or we may if we have time. That's a good question. Yeah. That's right. So what we're going to do is we're going to add this little piece that shows how the cosmic rays see the fluid velocity. That will lead to our final form for the cosmic ray distribution in phase space. Then we're going to take a moment of that, an energy moment of that, and that'll give us our equation. So we're actually almost done with this particular model. Yeah.
I was wondering if you could comment on the origin of the cosmic rays and why they're so separated in energy scale from the purple gap.
Yeah. So the main thing that we know, so the first, sort of important quantitative theory of cosmic rays was Fermi's theory. And Fermi suggested that actually this was sort of his acceleration mechanism, and he assumed that this occurs due to kind of random turbulent motions in the interstellar medium. So he had cosmic rays scattering off moving fluctuations and statistically gaining energy. There's an argument against that, which is that, so we can measure the confinement time of cosmic rays in the galaxy by the fraction of light elements, lithium, beryllium, and boron. And when we do that as a function of energy, we find that more energetic cosmic rays have a shorter confinement time and therefore on average are younger. But if cosmic rays were accelerated by some sort of continuous process in the interstellar medium, you would expect the most energetic cosmic rays to be the oldest. Instead, they're the youngest. So what we now think is that they're accelerated in special regions, either around young supernova remnants or in, so there's a tendency for massive stars to be born in clusters, and the sum total of the radiative output of those clusters is a so-called superbubble, which is formed by the luminosity in winds, and there's some, it's possible that some fraction of cosmic rays are also made in superbubbles. So superbubbles and young supernova remnants. Yeah. Could you repeat your question? I'm not totally getting it.
Function of S and mu, where it went from the function of X and P to the function of mu.
Right. So the most general form. So let's ignore the X and the, let's just look at the P dependence. Will that answer your question?
Yeah.
Okay, so we start with vector momentum. And then we can write that as a function of the momentum. So we could write that, as all three components, Px, Py, and Pz. And let's say that this is the parallel component. And then gyrotropy says that the dependence on px and py is the same, so it becomes a function of parallel and perpendicular momentum. And then p parallel is mu p, and p perp is 1 minus mu squared to the 1/2 of p. So then we just write it as a function of magnitude of p and mu. Does that make sense?
Okay, so the Boltzmann equation then, it only changes the u dependence.
So the scattering term, so far we've only allowed the scattering term to change the mu, but not p itself. But when we consider fluctuations that are not static, there'll be a little electric field that accompanies them, and then the magnitude of p will also change. But the main effect is the pitch angle scattering. That turns out to be a much bigger effect, and I can explain why. And I will tomorrow. Basically, it's because these fluctuations move slowly compared to the speed of light. They're MHD fluctuations. Okay. So I guess we're ready for lunch.